guys. In this video, I want to discuss the energy storage ability of capacitors. So capacitors are devices which allow you to build up charge, to store charge. You can use them for all sorts of purposes, electrical purposes. Maybe you use it to stabilize a current. So if you had a current that was noisy and maybe when it swung high or low, you could draw off any needed charge from a capacitor, kind of level things out. There might be many uses. Another way that capacitors are used is as energy storage devices. So people are exploring using capacitor ideas for quick charging batteries, or if you ever had an old-fashioned film camera with a flash bulb, what would happen is you would charge up a capacitor and then you would release it, and when it flashed, it dumped all that energy into the bulb, causing the bulb to burn out, but in the process giving you a flash for making a photo. So capacitors have lots of uses. This is one of them. So what we want to do is understand the formula for the energy stored in a capacitor. And to do that, you have to think about how we charge up a capacitor. So if you have a capacitor like this, what happens is, you hook it up to a battery or something, and a little bit of charge gets added on one side, which draws out the opposite amount on the right-hand side. And then you add a little bit more charge, and then it draws out a little bit more of the opposite sign charge. And you keep adding a little bit more, and it keeps drawing and drawing and drawing until you end up with a large pile of charge on one side and an opposite amount on the opposite side. And eventually, if you try to add any more, you can't, or the battery isn't strong enough to, because every bit of charge that you add on each plate, well, charges don't want to be near other like charges, which means that for them to accumulate on one side, something had to push them there, do work on them, and put them in place, which means after you have charged it up, there's a lot of potential energy stored in this, because the minute you would cut the battery off, or drop the or remove the voltage that's kind of that voltage source which is acting on them, those charges are immediately going to unwind and release their energy back into the circuit. So let's think about that process with some equations. So you can imagine that as you add in a differential amount of charge, dq, that after you've added it, there is a little bit of potential energy, a little bit of extra potential energy. So I would say a little bit of extra potential energy, du, is equal to dq times the electric potential. Now the electric potential, so, and to be careful here, dq is what is the observer, right? This is the charge who is experiencing the presence of other charges. V is the potential created by all of the previous charges that are already in place. So, okay, that's fine. And what you would imagine then is that's a function of charge. So as you add more charges, the potential sitting there that they generate varies. To proceed, we want to use the formula. We want to say that Q equals C times V, or flipping it around, V is Q over C. So we can, using that and then integrating up, we find that the energy stored in a capacitor equals the integral dq of Q over C. forming the integral, we find 1/2 q squared over c. Now, my lowercase q was my variable q as I accumulate more and more and more. But the final charge, I'm going to write with a capital Q, just keeping consistent with my constants being capital and things that are variable or integrated over are lowercase. Now, it's convenient to use this formula to rewrite this. So I could also rearrange this to say 1/2 C times the voltage squared. And that's a handy formula to have. So if you want to, you can think of the energy stored in a capacitor in terms of its charge. You can also think of it in terms of its voltage. Okay. Now, an interesting observation. Note what happens. So we found that the energy in a capacitor is 1/2 C times V squared. But for a parallel plate capacitor, we also have that V is equal to the electric field times the distance across the capacitor. That's a special result for a parallel plate capacitor because the electric field is constant, and so the electric field is simply the slope of the potential. Now, you might be worried about a minus sign. The formula I'm after here is for the magnitude of things, so it's not going to matter. Ultimately, we're going to plug it in here and square the voltage. So if I rearrange this, I learn that U equals 1/2 C. But what was the formula for C for a parallel plate capacitor? That was the area times epsilon naught divided by D times the voltage squared. That will be E squared times D squared. We can rearrange that a little bit. A convenient thing is, rather than studying the total energy, let's study the energy density or the energy per unit volume. So that would be lowercase u, the energy density, equals capital U over the volume. But the volume of a parallel plate capacitor is simply the area times D. So that's going to give me epsilon naught over 2 times E squared. If this was a movie, there would be music playing right now, because we have just completely changed our picture of reality. You might be saying, huh? But here's what we found. We can think of the energy density stored in a capacitor. We've been talking about it in terms of the voltage or in terms of Q, but in fact, that's not really right. In fact, when you work out the energy density, so the energy as it's spread all out, you find that it doesn't go like the charge, or maybe what you might have guessed, the charge density, sigma, or something like that. In fact, it goes like the electric field squared. So that's quite interesting. What that implies is that the electric field has energy associated with it. And if you think about how we arrived at the concept of an electric field, that's really bizarre. Maybe not bizarre, but just surprising. Because for us, we first encountered the idea of an electric field more as a mathematical trick. You know, it was just a way of breaking a complicated force problem into a piece that we could solve, and if the rest that we could handle later. But in fact, that's not right. The electric field is a real thing insofar as it carries energy, and later we'll see it also carries momentum. So it's every bit as real as the charges we started with. So if you're kind of keeping track, it's kind of like we've been playing this game, talking about charges and forces on charges and fields they produce, but mostly all about charges. And what we've just learned is that the number of players in the game are twice as big. Not only do you have charges that are real, carry energy and have properties, the electric field has all of those same, well, it doesn't have charge, but it has energy and momentum. It's just as real as anything else. And so it's kind of a first foray into a wider world, the world of field theory. And we ultimately, in fact, the final picture, the final story is that, in fact, the charges that we've been pretending were little points, in fact, they are also fields kind of spread out like the electric and magnetic fields. So that's it's kind of an exciting point. If you didn't know about this, the world is much richer and wilder than what you would have thought before hearing this. Oh, and you might be wondering, I got this formula from using parallel plate capacitors. But actually, if you think about it, what happens in a parallel plate capacitor is that the electric field is constant. And nothing else really depended upon the details. The energy density was independent of any of those things because it was an intensive quantity. The thing is, any other electric field, it have bends and curves and stuff like that, if you zoom in close enough and talk about how it behaves locally in the middle of it, well, then you're going to use intensive quantities to describe the local information. And if you zoom in on any profile enough, it looks constant. So this formula, although derived for a parallel plate capacitor, must also be true even when the electric field is buried. So it's kind of a profound result, and it really changes the nature or our conception of what is real and what is reality. All right, so next time we will start talking about dielectrics.